Good morning. Hello.
Good morning.
Oh, so you can hear me. That's good. How many people are in here today? Oh, maybe we shall give your colleagues a few minutes before we start. Please mute your mics. Those who are not muted. Let me just mute you. Good morning once again. I don't think the numbers are increasing as fast as I thought they would. So I'll just start. The rest will find us as we go. Apologies for those who tried to join last on Monday and couldn't. I don't know what happened because I set up the meeting to allow you to enter automatically. But these things happen with software. So, and we were not able to record on that day. But what I've done, I've sent Israel Nigadi a link to Khan Academy. You can search for it yourself. They have a good presentation on, good lessons on Laplacian. So if you just get that whole topic and listen, I think you'll be able to get up to speed with what we covered. Yeah, that's to repeat, but we cannot repeat. We have already lost 2 weeks, which is the first 2 weeks of the semester because people are striking, they're not striking, so I don't know. So we cannot really go back. But hopefully, if you go through the Khan Academy, those people who are not able to join, if you go through that and you still don't understand, feel free to send me an email and we can have some consultation. So for today, we are going to move forward. I think last time we stopped on slide 50. This was a problem that I asked you to go through. I don't know it. For those who tried to go through it, did anyone find any problems? Any challenges?
No, it was okay, madam.
Okay, that's good. So I think we'll move to the next page. Okay, this is still just a summary. This is our reference table. The one we need to keep looking at to figure out if we need a reminder on what transforms we have. So I think we also went through this as well. I'm not sure, but briefly, the advantages of the Laplace method, I talked about it last time. If you have non-homogeneous ordinary differential equations, you don't need to first solve the homogeneous ODE. And just a quick reminder, homogeneous ODE is one where you equate it to 0, so there's no input. And the non-homogeneous one is one which has an input. So the way you learned in first year, I think you had to first do characteristic equations, equate the non-homogeneous one to 0, get those solutions, and then work out the non-homogeneous equation. Here, as you saw, you'll do it directly. Initial values are automatically taken care of. You just substitute them in those equations in here, SF0 and the derivative of f at 0. So these are the initial values. These two will be taken care of, and yeah, complicated inputs will be handled efficiently. So I think we have some other examples. We didn't look at this one. So here we have an example where the initial value isn't it's at a value greater than 0. So we have this differential equation, okay? And the initial value that we are given is y, a quarter pi, is equal to a half pi, and then the derivative at a quarter pi. So our initial value is a quarter pi. So what we usually do for such a problem, we'll set our t equals to I'll call this t tilde plus t naught, okay? So that t is equals to t naught if this t tilde is 0. In our case, it isn't 0. So in our case, t naught is a quarter pi. So our actual t is going to be t tilde plus a quarter pi. So we go ahead to solve our equation, and we again present this as we put this tilde sign at the top. So what is t here? We are going to substitute with our t tilde plus t naught. So in this case, it will be t tilde plus a quarter pi. Then with regards to our y tilde, our 0, the value is a half pi, okay? And our derivative at 0 is going to be this value at what would be at when t naught is equals to a quarter pi. So these are the adjustments we make, and then we solve it more or less that we would solve using, we make these substitutions up here at the top, okay? These are the values we have, we were given in the question. So we do our expansion of derivative squared and of dy dt with Laplace. I hope you remember this transform. We are essentially using this equation, this one. And once we substitute in the values and put things on the left side with y and everything else on the right side, we'll end up with this kind of formation, okay? At this juncture, I hope you can start to see familiar things. S squared plus 1, S squared plus 1 in the denominator should tell you something. Here we have again S squared plus 1 over S. So if we go back to the different, to our table, the one I showed you, table 6.1, I think, you can get the inverse of all these terms and you'll end up with this expression, okay? So, but we then have to go in and make our substitution. We initially had t tilde is equals to t minus a quarter pi, remember? So if we have sine t tilde, then we have to make this substitution. So we can simplify these. Some of the terms will cross out, I think. If you expand this, some of these terms cross out. Already they were, some of them actually were cancelled out. You end up with 2t tilde plus a half pi minus root 2 sine t tilde. So if you replace this t tilde with this, then you'll end up with y is equals to 2t, because if you multiply 2 plus times a quarter, you'll get a half pi minus a half pi, which will cancel with this half. So you end up with 2t. And then if you put it in here, you have to, if you do that expansion, sine A minus B, I think, you'll end up with sine minus sine t plus cos t. Remember, I told you have to, a lot of those trigonometric identities come in random places. So you have to be on the top of your game for some of those. Here they use a sine, because you're going to put in here sine t minus a quarter pi. So if you use, if you have sine A minus B, it's going to be sine A cos B minus sine B cos A, isn't it? So you'll end up with this cosine t, you'll end up with 1 over root 2, because sine a quarter pi is 45. Sine 45 and cos 45 are both 1 over root 2, okay? When you multiply it by this other factor up here, we had by this root 2, the root 2's will cancel, so you'll end up with just sine t plus cos t. And that way you'll have catered for the fact that the initial value, they gave an initial value of a quarter pi, but by making this substitution, if I may call it that, make t equals to t tilde plus t naught, so that you can keep your initial values here as 0. If you consider it on the side of t tilde, it's going to be 0, okay? It's t naught that's a quarter, but t tilde is 0. So then you can still use the same equation we used before and work out, make your simplifications, and you will get y equals to 2t minus sine t plus cos t as your answer. I'll leave this here for you to just look at, and if you have any questions, please ask now. Okay. So next we are going to look at what unit step function. I don't know if you have, I don't remember the syllabus is for first year. I don't know if you've looked at unit step functions before, but these are very common in engineering applications. I know for communications, like, yeah, they're everywhere. So they're sometimes called that, this unit step function, sometimes called the Heaviside function. So we are going to also look at the Dirac delta function. So the unit step function or Heaviside function is denoted by ut minus a. And then the Dirac delta, which we'll look at afterwards, is denoted by this delta sign and t minus a. We'll look at it next after looking at the unit step function. So yeah, step functions, you can read this. They are like, they help us to model very many engineering applications, which have, especially those that tend to have a kind of on-off behavior. I know that we use it a lot in communications to model like square waves, which kind of have the, like you have 1, 0, 1, 0. So they are used for that, but not only that, they're used a lot also in filter design and so many other things, even in these other engineering, other types of engineering, like mechanical engineering and civil engineering. I don't know the applications, but just so you know, there are so many applications of, of these functions. So also discontinuous. So you could have like a sine wave and you apply it for, say, 1 period. But the way we model that again is we use these Heaviside functions, and we will see some examples shortly. Okay. Yeah. So diagrammatically, this is what it looks like. If you look at figure 118, essentially it's ut is the same as ut minus 0. So for it, it is 0 before 0, and then from 0 onwards, it will have a value of 1. So it's like a, one step from 0 to 1. It will keep them 1 to infinity. And if you have, look at figure 119, where it's written as ut minus a, the a denotes a delay. So if a is equals to 1, then it will move from 0 to 1 at 1. If a is equals to 2, then it will, before 2, it will be 0, and then after 2, it will be, from 2 onwards, it will be 1. So this is what it looks like. I mean, visually, you can see that why they call it a step function, because it's essentially like you move from 0 to 1, so it's like one step. And yeah, this is this definition. So 0 if t is less than a, and 1 if t is greater than a. So it has a bit of a jump, and that's why this liner is broken. If you look at the line at a, because it at the value a, it doesn't have, it's both 0 and 1. So usually it's just defined for 0 for less than a and 1 for greater than a. At a, you might say it's undefined, because it has it's the point at which it steps, it goes up to the other value. So it's usually undefined at that. And it's assumed that a is greater than or equal to 0. You will see that for most examples, you'll do that's the assumption, because we tend to deal with causal systems. We want systems where we know that it only starts to give output when something is applied. We don't want a system that essentially, if a system isn't causal, it's like it will have an output even when there's nothing being applied to it. So it's, most of the time, it's something that you can't control. So you'll find a lot of this assumption in the sense that this also has an element to do with whether a system is causal. But that's a detail. You don't have to know that. I'm just giving you extra information. Hopefully it helps you to understand why this is important. Anyway, so this is how it's presented. This is what it looks like. So that the minus a usually presents some kind of delay. If it's equals to 0, then it will be at 0, like figure 118. If a is any number greater than 0, then it shifts, the step shifts to the right. And because a is always greater than 0, it's always going to be a shift to the right. Don't expect it to shift to the left. For the applications we'll look at anyway. So what is the Laplace transform of ut minus, of this step function? It's relatively straightforward. If you've done your integration, you can see from 0 to infinity, but because the plus is defined for 0 to infinity, but we know our step function starts from some value a. So when you've done the integral, this step, your limit's actually going to be t is equals to a to infinity, because anything below a is going to be 0. And anything a and above a is going to be 1. So that's why you see it's replaced by this 1 here when you're doing the integration. And yeah, once you integrate this, you'll end up with e to the minus as over s, which is, I think, what the Laplace transform for 1 is 1 over s. So here, what the delay then introduces this this term e to the minus as. I don't know, people who have video on, do you mind switching it off? I find it distracting and I don't think it's necessary. If you have video on, please switch it off. I don't want to name names, but I would prefer if you don't have video on. Okay, so yeah, what else did I want to say? Who is this person? Is it someone who is on a Galaxy S1? Could you please switch off your video? Anyway, yeah, so it's usually used to model functions that involve on or off. I think I mentioned that earlier. Yeah, so multiplying a function, any function ft by a step function can produce all sorts of effects. And I think instead of reading here, I could just show you some of those figures. So if our signal is a, ft is 5 sine t. This sine wave, the first one, this is a normal sine wave. If you multiply it by step function ut minus 2, so a step function delayed by 2. By the way, usually when we have any function, if it's a time function and you have minus 2, minus a, anything, we consider that a delay. So every time you hear me saying you delay it, I'm referring to the fact that this is ut minus 2. So if you delay it if you multiply it by a step function delayed by 2, you'll see that it will cut off the first part of this sine wave. So the output is actually going to be this part starting from 2 up to pi. Okay. Then if you also delay this function by 2 and then multiply it by a step function, which is also delayed by 2, you reproduce it, but it will be shifted. So it will, instead of starting at 0, the function will begin at 2. This is what they call delay. And this is what they refer to as delay. So if both of them are delayed, then you'll be able to recover the same signal, but it will only have started, say, let's assume these are seconds. So it will have started 2 seconds later than the original signal. What else did I say here? Yeah, this just is what I just said. Yeah. Another example is here. Here we have, with A, we have a number of, it's just a summation of different step functions. So the first one is a step function delayed by 1, okay? So it will go up, and then we subtract twice ut minus 4. What that does is, this one was 1, it's going to be minus 2, so it's going to go down to, remember we have this k multiplying the whole thing. So it's going to be k minus 2k, so you end up with minus k. And then that goes on up to this t minus 6. So t minus 6 doesn't have any 2 here, it only has 1. So its effect is going to be to move from minus k to plus k, so it will go back to 0, and then it will continue on as 0. It's unfortunate I don't have a blackboard, so I don't know if you can visualize this. But imagine all these ut minus 1 is a function that starts at from 1, sorry, from 1, it goes on infinitely as 1, has amplitude 1. Then ut minus 4, because it has a negative sign, and it has times 2 in front of it, is a function that is going to be minus 2. So it starts from where the other one stopped at as 1 minus 2, but this minus 2 is also going on infinitely. So this third step function, ut minus 6, wasn't there. This would go on infinitely at this value minus k, because it would be like minus 1 times k. It would be minus k. But because you're now adding another unit step function, which is now positive, it's going to be like another 1 or 1 times k, which is minus k plus k. Then you set it back to 0. So by doing different combinations of step functions, you can produce a square wave and different types of square waves. It could be a square wave where it's just going from 0 to 1, 0 to 1 periodically, say every after 2 seconds. It really all depends on what kind of manipulations you make. So for these ones where it was UT, I did 1 delayed by 1. Could you please mute your mics? We really don't want to hear what you're doing, and I don't know who that is. You're even hearing this. Please switch. All of you, please mute your mics. So anyway, 1 is delayed by 1, the other one is delayed by 4, the other one is delayed by 6. If you add them up, you end up with this kind of thing. In this, in B, we have a sine wave. Okay, sine pi over 2t, but it is multiplied by ut. So from 0, here we have ut minus 2.
Excuse me.
Yes.
On the first example we have in the figure 121, I'm seeing when we multiply the kth root, at the second function we would have negative 2k. And according to the representation, it's as if they are giving it just negative k.
No, you say you're applying negative 2k when you're at k. What is k minus 2k?
Oh, yeah.
Okay.
I've seen it.
Okay, that's good. So for the second one, from 0 up to 2, we have 1. Okay. Remember, it has 4. It has an amplitude of 4, so it's 4 times. So that's why the amplitude. So, but then at time t, we subtract ut minus 2. So that's why at time t minus 2 is going to go to 0, because you're going to have 1 minus. Okay. Then at time at t is equals to 4, it's going to become 1 again. Okay, so you'll take that, and if you subtract ut minus 6, which is what they did here, then again it will go to 0. Then ut plus 8, sorry, ut minus 8 will again take the upper part of sine wave. So by adding these different step functions, you can create these different patterns depending on what you need or what kind of system you're trying to design. Okay, this is what they were talking about, how you can use these step functions to produce different types of, say, input signals, okay, for different systems. This is how it's done. It's just a summation of different step functions at different delays intervals. Does anyone have a question?
Excuse me, madam.
Yes.
Okay, thank you for the lecture.
There's no need, but first of all, there's no need to thank me. Don't worry, I'm being paid.
Where are you getting from?
Yeah. Cannot hear you.
I'm saying I'm not getting where. I'm saying I'm not getting where that negative is coming from.
Which negative? Minus ut minus 2?
For the, yes, like now for the first function in A, I'm saying minus 2u into 2 minus 4. And then for function B, I'm saying minus u into t minus 2, and other functions we are adding. I just want to get the origin of that.
Oh, but which minus? You see there are two minuses. There's the one inside the brackets and there's the one outside the brackets between the two step functions. Which one are you asking about?
It is that negative outside the bracket.
The one outside the one outside the bracket, that's what I was saying. It depends on you. What are you trying to find? Okay? If I want a step function, okay, of this type. So for instance, this person they wanted a square wave, I mean a bit of a square wave from 1 to 4, they wanted a square, okay? On the top side of a positive, okay? Then from 4 to 6, they wanted a negative, what should I call it? Negative step. So it depends on what you want to do. Because I could even, this thing might have been multiplied by 3 and gone down to minus 2k. It depends on what system you're designing and what you want to achieve. Okay? So in order to get this look, they had to do this. In order to get this sine wave, they had to do this. Because you have to remember that if you want to cut off this signal, you have to subtract a step function from another step. It's the same as saying 1 minus 1. However, the difference is for one of the functions, it became 1 at 0, and at 2, you're subtracting another one. So it's like you had 1, and then at 2 you're bringing minus 1, so it's going to be 0. Between 2 and 4, if you look at figure B. So between 0 and ut is active, so you have 1. At 2, if I subtract ut minus 2, I've introduced a negative 1. 1 minus 1 is going to be 0, and that's why it's flat. At 4, I bring another step function. So it's going to be, what I have now is 1 minus 1 plus 1, which is now plus 1. So the wave will be there. At ut minus 6, another negative. Then I'll have 1 minus 1 plus 1 minus 1, which is 0. All you're doing is you're introducing either a positive 1 or a negative 1 at different time intervals. Every time you say, let me just go back to this figure. So if, let's look at this actually, this is a good example. This is ut, okay? If I say minus ut minus a, what's going to happen is when we reach time a, you have a flipped, this thing is now negative. So if I had to draw the minus 1, it would start from the negative of this. It would start from a and go downwards. But if I add ut, that is positive 1, and I have minus ut minus, if I add them, it will end up going to 0. Because one will be minus 1, the other one will be 1. Imagine if you brought these two on the same graph, but this one is flipped because it is a negative. If you put a negative in front of it, the x-axis will be like, or the t-axis is like a mirror. If you put a negative here, it will be the exact, like it will be a mirror image, but on the opposite side of the axis. So imagine if you flipped it and brought it to this other chart. So this one would continue being 1, but this would be minus 1 from A. And they would cancel themselves out, so you end up with 0. I don't know if that makes sense. So the person who asked the question, I don't know if that makes sense.
I've got it, madam.
You've got it? Okay, that's good.
Yes.
Okay, so because we need to move, it's already past. Okay, so we are now going to look at what the issue is of these step functions on our Laplace transform. So we have the time shifting or T shifting theorem. So what this says is if I have a function ft with Laplace transform, then this is the first one we looked at earlier. Then fs minus a is equals to Laplace transform of e to the power at ft. This second one, again, is going to now have to do with in time domain. What is the Laplace transform? If I have ft, what is the Laplace transform of ft minus a? And so this is the second time shifting theorem. So if ft has a transform fs, then the shifted function, which is ft minus a, we usually multiply by this to show that it is 0 up until a. So we'll have is 0 if t is less than a, and it is ft minus a if t is greater than a. It has this transform. It has the transform e to the minus as fs. So if I have a function, and we'll see some examples, I know the Laplace transform of a function, say 1. 1 Laplace transform is 1 over s. Okay? Then if I have, that 1 minus a won't work. That doesn't make sense. We will look at another example. 1 isn't a good example. So anyway, so if the Laplace transform of ft is fs, then the Laplace transform of ft minus a multiplied by a step function is going to be e to the minus as of fs. And if we take the inverse of this, e to the minus f, we'll be able to recover our function ft minus a times the step function. I think, yeah. So this is an example, I think. Yeah. So if you have a function 5 st, okay, its Laplace transform, 5 sine t, is Laplace 5 over s squared plus 1. I hope you remember this. The Laplace transform of sine t is 1 over squared plus 1. So if we shift this, if we say our function is now sine t minus 2 u minus 2, which is given by t. So if this is our new function, then its transform, okay, is going to be exponential to the power minus, we have minus 2, so it's going to be minus 2s fs. So we'll have to multiply this by exponential minus 2s. That is what the theorem essentially says. If you know the Laplace transform of a certain function and it's shifted and multiplied by a step function, then the Laplace transform of the shifted function is just going to be a multiplication of an exponential to the power of the shift. In this case, it's minus 2 and then times s. That's what we have here. And we can prove the theorem for those of you who want to. It's really simple. It's just simple integration. Okay, so we have e to the minus e to the minus as of fs. Okay, we pull out this and we are doing what? Yeah, we are substituting fs with the Laplace, because we know it's the Laplace transform of some ft. Okay, we are using tau here, but it might as well have been t, and if it still have been, okay. We just want to end up with t here. So we've replaced it with, we first use tau, because we're going to substitute for t with this. So initially we use tau here and expand here. We're going to bring in this s inside here. So we end up with minus s here, tau to the whatever. Then we replace tau plus a is equals to t. So tau is equals to t minus a, and the tau is equals to dt. I hope you remember these things. This is HSC math. And in the integral, yeah. So you end up with, if you replace with t, you end up with this. which from the theorem, if you remember, is, yeah, if you see it up here, this is what up here. This is the Laplace transform of this. But you don't have to worry about these proofs. I will not ask you to prove anything, but for those who are interested, you can look at them. Okay. I'm not going to go through it, but for those who are interested, you can go through it. I will not ask you to do any proofs. That is a promise. So we have an example here. Write the following function, unit step functions, and find its transform. Okay. You have ft. Anytime you have a function which is defined this way, that they tell you, okay, it's between 0 and 1, then it's a half t squared between 1 and half pi, then it's cos t between, for anything greater than t. Then you know that you can write it in terms of step functions. And what it's going to be is, for the first part, it's really going to be, you'll that you have 2 from 0 to 1. So we write that as 2 into 1 plus ut minus 1, the step function delayed by 1. Okay. Then for this one, it's from 1 to a half pi. So you should expect that you're going to have ut minus 1. This is where it starts from, minus ut minus half pi. And then lastly, which is the cos t, was the one for anything greater than a half pi, I think. Yes. So for it, it's going to be multiplied just by ut minus a half pi, because it goes on. So there's no subtraction here for cos t, because it doesn't, it continues on up to wherever the function stops. If you can look at this figure, above t just continues being a sine wave. That's the discontinuities are here for 2 and for t squared. Okay, that's why we have the subtraction of step functions for those ones. So in step 1, we have written them this way. So the next thing is based on our theorem, which we have just learned, is if we know what the transform for ft is, then if we have ft minus a times ut minus a, we know, we will know what its the expansion is. So for 2 times 1 minus ut minus 1. For this one, we just know that it's going to be the Laplace transform is 1 over s. Then for 2 times ut minus 1, we know it's, again, for 2, we know it's 2 over s. But then we have to multiply it by e to the minus s because of this term and this minus 1. So it's what brings the exponential. For this term, which is the half t squared, this difference of Heaviside function, we will expand each individually. First, we do a half t squared into u t minus 1. So if you expand this, oh, actually, we need to, the challenge here, the trick here is we need to put this in this format. We need to put it in a format of ft minus a times ut minus. And how we did that for this one is we have a bit of completing squares. So we have t squared, but we have to make it t minus 1 squared so that it has this t minus 1. So we create t minus 1 squared. However, we need to cancel those extra terms. So t squared, t minus 1 squared, you'll have an extra, 2 extra terms. So you have the 2t divided by 2 and the plus 1 divided by 2. I don't know if you get that. Because we are trying to get this t squared to have this t minus 1 squared, we have to cancel them. That's where this t minus 1 comes from and this half comes from. Because if you expand this, it should end up with only t squared. But when we put it in this format, okay, then if you multiply, if you have 1 squared times ut minus 1, then its transform is just 1 over s cubed. For this one, again, t minus 1, the transform is 1 over s squared, and then for a half is 1 over 2s. And of course, we have to add the e minus s from this. Same thing when we go down here. Again, we need to make this t, put it in the format of t minus a half pi squared. And then again, we have to also have a term t minus a half pi, and whatever stays is what we pi squared over 8. Once we put it in that format and we have our u t minus a half pi here, then our Laplace transform is easy. Again, we'll end up with 1 over s3 squared, pi over s squared, pi squared over s, and our e to the minus pi s over 2. I'll give you a minute to look at that. And if possible, actually, you could try to expand this and see if you could try to expand the first one. Okay, if you can do one and get this result, then you will believe that also the second one works. This is when I wish I had a blackboard. I think I need to look for some tools. But just try to expand this t minus 1 squared and t minus 1 and see that you'll end up with a half as that if you expand this, actually just try to expand this and see that you'll end up with t squared if you cancel out like terms. So you should be able to convince yourself that this that is in this bracket is actually equal to t squared. We're just putting it in this format to make it easy for us to do the Laplace transform using the known transforms that we have. Does anyone have a question? Yeah. So the last one is actually the cos t into ut. Even for this one, we manipulate it again and replace it with a sine t minus a half. Yeah, again, if you expand this, you should go back to this. And once you do this, then you can replace, the Laplace transform is easy. I mean, again, it's in a format that we can easily transform. So putting it all together, you end up with this as the Laplace transform. Having applied this rule, the second shifting theorem. Take the time to go through these examples. They might look difficult, but if you spend the time to try and just go through them, they're not that difficult. It's just a lot of integration. In fact, in this case, it's just a lot of what should I call it? Algebra, just manipulating numbers to make them put them in a format that kind of suits your needs. There's no real manipulation here. There's a bit of trigonometry because you know sine A minus B is sine A cos B minus sine B cos A is what they used. That's it. So if you can remember those few tricks, I think it will be okay. Those of you who don't get it now, I hope you'll go back and try to go through it. Because of course, when people are writing this book, don't write all the steps. Don't have a blackboard. Okay. Oh, okay. This is another way of working out that same get those same results, but this is a kind of a shorter route. Okay. So by writing ft minus a as dt, which implies that, so by writing your ft, if you say ft, if you equate ft minus a, shifted f to some function gt, t is going to equals to gt plus a. Okay, so you have a half t squared ut minus 1, then it's the same as our a in this case is equals to 1, and ft is equals to t squared. Okay, so if you use this same approach, then you will make it a half t plus 1 squared, and you'll multiply it by e to the minus s from this ut minus 1. Okay, and then again keep e minus s out, do the expansion of t plus 1 squared, which is t squared plus t plus a half, because of this a half out here. So it will be a half t squared plus t plus a half. And then this is more straightforward because you know what the transform of t squared is, you know what the transform of t is, you know what the transform of a half is. So it's a bit more straightforward than the method showed before earlier. But to get to this one, you just have to make this change where you say you equate ft minus a, shifted f to some function gt, and then you, okay, so if ft minus a is equals to gt, then ft is going to equals to gt plus a. Then make these substitutions. So this one is more straightforward than the technique shown on the earlier slide. You'll do the same thing for this other function as well, which was a half squared ut minus a half. Here you have e to the minus pi over 2s, and then everything else will stay the same, because again you'll have t plus 1 squared, so you end up with e to the minus pi over 2s, and then 1 over s squared plus 1 over 2s. For cos t, same thing. With its ut minus a half, you have e to the minus pi s over 2, then Laplace transform of cos t plus a half. Okay, this one again you will use the trigonometry. I think for cos a plus b, it's cos a times cos b minus sine a times sine b. The cosine part will go to 0 because cos pi over 2 is cos 90, which is 0. So the sine part is what remains, and it's a negative. And yeah, so the Laplace transform of minus sine t is again minus 1 over s squared plus 1. So this is a bit more straightforward. And if you prefer, you could use this one. I find it a lot easier than this one, which has to do with expansion. Does anyone have any questions? None? Let's move along. So another example, find the Laplace the inverse transform of this. So if you look at this closely, and it should look familiar for some. Remember, we are still applying S15 here, but look at the denominators here. We have s squared plus pi squared. Okay, the top we don't have s, so this is most likely a, but we have to do some manipulation to it, because ideally you would expect pi up here. Ideally you'd expect pi over s squared plus pi squared. If there's no pi, then it means it's like I'm talking about this one. So because we don't have pi in the numerator, this must be sine pi t over pi, which has been divided by pi. I hope you guys can see that. Because if it was just sine pi t, there would be a pi up here. But because it's missing, because we have one here, then we say, okay, this must be sine pi t over pi. Think for the second term, okay? The third one is s plus 2 squared. This one, if you remember the transform we looked at last week, I think it was the first shift. Anytime you have this plus 2 down here, plus with s plus something, it has been multiplied by some exponential, which is what is here. Okay? S squared is the transform of t. So you see we have t times t, just by inspection. However, now we have this e to the minus s, e to the minus s, e to the minus 3s. People who are talking, please switch off your microphones. I will just kick you off my mute. Let us wait for those who are discussing. Okay. If you start talking, I'm just going to remove you from the class because I don't understand why people don't mute their mics. It doesn't make sense to me. Anyway, so by inspection, we know what terms we're looking at, but now we have these exponentials here, e to the minus 2s, e to the minus 3s, and e to the minus s. Okay? So then we looking at this theorem, the s shifting one, okay? We should know that these have been multiplied by some step function. So at the end of the day, we will know that this is sine pi t minus 1 times ut minus 1, simply because we have this e to the minus s, okay? For this other one, it has e minus 2s, so we'll know again it's shifted by 2 and multiplied by ut minus 2. This one minus 3s, so it's shifted by minus 3, t minus 3, and then again also multiplied by so that t is minus 3, or everywhere where there is t, you have to add a minus 3. So for this one, you have t minus 3, then e to the power minus 2, t minus 3, and then you multiply it by the step function. Does anyone have a question in this example? Okay. So this is a simplification. Yeah, the simplification of this is sine pi t minus pi, which is minus, end up with sine pi t, and sine, okay, minus sine pi t. I don't actually remember these things, but if you have, say, a function, say you have 45 minus pi, you'll end up with what? I think it's minus 135, which then ends up being a negative sign. Okay. Any angle that you have, if you subtract pi, the sign will become negative. So if it was positive, it will become negative. If it was negative, it will become positive. That's what this means. Then if you have sine pi t, any number times minus 2 pi is going to be the same number. So sine pi t minus 2 pi is equals to sine pi t. So when you add them up, this and this will cancel out. So what you end up with is that let's first go back to the definition. Yeah. So for t, as you can see, this term comes in when t is equals to 1. So first of all, for anything less than 1, you have 0. For t is equals to 1 to t is equals to 2, we're going to have this sine pi t. Okay? That is what you see in this figure. Then between, you'll see that at t is equals to 2, this other sign comes in. So you have this sign from t is equal to 1, and also this sign, okay, you have these two sign functions both in play. But because one is as you see from this up here, one is minus sine pi t, and the other one is sine pi t. They will cancel out. So that's why between 2 and 3, you have nothing. It will be 0. And then from here, our solution, this last part comes in when t is equals to 3, is when it's activated. So this term is what you see plotted here from t is equals to 3. This exponential will then come into play, and it goes on and keeps us. I hope you remember what exponential functions are like. They just tend to, as you go towards infinity, they tend towards 0. So that's why you see this this curve. I don't know if you have any questions. The one thing you have to realize about step functions is if it's t minus 1, then it's 0 anytime before 1. If it is t minus 2, it is 0 at any point before 2. T minus 10, it is 0 at any point before 10 and 1 after that. So that should help you figure out which of these is active. So at t is equals to 1, this is 0 because it's ut minus 2, and this is also 0 because it's ut minus 3. So at t is equals to 1, only this term is, this sign function is activated. When it hits t is equals to 2, both this one and this one are active, but they cancel each other out. So that's why between 2 and 3, you'll have 0. Then beyond, from t is equals to 3, this one will also be activated. That's what's happening here. Does anyone have a question? Please feel free to ask questions. I think there are no stupid questions. I think video should make it better because people can't see. If you're worried about asking, no one can see you. So if you have a question, please feel free to ask. Yeah, I think it's better to ask here, then everyone gets to also benefit, because sometimes people haven't thought about that question, but when you ask it, they also get a chance to understand, and also get a chance to understand what you don't understand. So are we good here? Yeah?
Excuse me, madam.
Yes? Who is speaking?
Good morning, madam.
There's no need to greet
I
me.
was kind of request. Tilen.
Tilen, yes?
Yes, I was kind of requesting you to help clarify further on that point that you made about if it's t minus 1, you said before any point before 1 is 0. It's t minus 10, any point before 10 is 0.
Yes, because remember,
If you can throw a little more light on that.
I'll go back up. This is what our step function, because we are multiplying all those terms by step functions. Okay? Tilen, you've switched off. Okay. We are multiplying all those functions by step functions. If you multiply a function by a step function t minus t, it doesn't matter, even if it's a sine wave, like sine t, okay? As long as t is less than a, it's going to be 0, because you're multiplying it by this point between 0 and a. This function, this step function, you're multiplying it by 0, and any number times 0 is 0. So the only point at which it will start to display is when you hit a, because at a, the step function is equals to 1. So it will bring out, then the other function you'll now be able to see a sine wave from whatever it looks like at point t is equals to a. So any step function, a is that gives you the time at which it moves from 0 to 1. If time is equals to, if the step function is ut minus 10, anything before t is equals to 10 is going to be 0. If you multiply it by any function, anything 0 is, t is equals to 10 is 0. And then you only start to see the function after t is equals to, because it's a multiplication. Does that make sense to you? Hello?
Yes, madam, thank you.
Does it make sense? Okay, that's good. Just always remember that
yes, thank you.
Anything by a step function. Anything before that number in the step function, if it's 2, if it's 100, if it's 0, if it's 4, the other function only becomes active after t is equals to 4. If it is 4. Anything beyond that is just set to 0. because of the multiplication. Okay, so now we are going to the Dirac. The next one we're going to look at the Dirac function, delta. Delta is used, yes, it's used in, like, there's some examples here, hammer blow, a ship being hit by a single wave, and all these different things. In communication, we have channel. In communication systems, I talk about communication systems because it's what I know most. But in communications, when we are modeling a channel, the channel where the signal passes, you send a channel from that, a signal from the base station or from any transmitter to a receiver. We usually model it using this kind of delta. We call them impulses. Whoever that person is whose mic can remove you from the meeting. So it's from the lecture. So this let me first remove this now. Has she gone? Anyway, so yeah, so it's used to model so many different things, but don't worry about that. For those who want understanding, you can read some of these things, but here we are mainly it's the mathematics we're interested in. So this function, figure 132 shows a representation of it. Okay, it's usually defined as 1 over k, some value k, and for the interval a less than t, less or equal to t, which is less or equal to a plus k, okay, and 0 otherwise. So unlike the step function that goes on as 1 to infinity from that point where it's activated, from that point where it's delayed, this one is only activated for an interval k. Okay, its amplitude is 1 over k, as you can see in this figure. But we tend to limit it to that k to 0. So usually when we draw an impulse in communication, it's just a line, a single line with an arrow facing up, because it's very small. Okay, and that's what this is. So the function represents an instance, a force of magnitude 1 over k acting from t is equals to a to t is equals to a plus k, where k is positive and small. Okay. In mechanics and also in communications, they say here in electromotive forces, yes, the integral of such a force is referred to as an impulse. Okay, just take note of that. And yeah, so this, if you integrate from 0 to infinity, we change the limits because we know it's only active between a and a plus k. So that's why they change the limits here. 1 over k, and the area is always equal to 1. What that means is the smaller k becomes, okay, then the higher the amplitude. Every time k becomes small, this thing becomes infinitely. So when k is equals to 0, its amplitude is infinity. It doesn't really make a lot of sense, but then it's a very good model for those, say like they talked about a wave hitting a ship, or in our channel modeling, it's a good way to model the channel, because essentially you have all these signals coming, when you send out a signal in communications, you send it out, it goes through multiple reflections and diffraction and all these things. So when it gets to the receiver, it doesn't come as one signal. You get different versions, because they depending on where they are reflected, the channel will introduce delays. So you get multiple copies with different power at different time. So, okay, this is a detail. Don't worry too much about it. Maybe even I shouldn't talk too much about it because we don't have a lot of time. Anyway, so yeah. So when we limit, we'd say, okay, as k tends to 0, okay, we will denote it by delta t minus a. This is usually what we use to, and is what is referred to as the Dirac delta function, or the unit impulse function. Yeah, this is the one that usually has a magnitude of infinity if t is equals to a, and it's 0 otherwise. So it doesn't make sense in the ordinary sense because usually integration, if you integrate from 0 to 0, you will get 0. So it's usually called a generalized, that's why it's referred to as a generalized function details. And always when you integrate it, the area is always equals to 1. So that's what equation 3 is all about. Yeah. So the thing about in here, it's called the shifting property. It has a shifting property that every time you multiply a certain signal, say GT, look at equation 4. If you multiply it by the impulse function, this by this unit impulse function, it has a, what it does is it like, in communication it's referred to as sampling, but here it's referred to as shifting, a shifting property. It will get you the value of that function at that time instant. So if you sample at time A, because here it's like the unit impulse function has been placed at time A, t minus 8 has been delayed by A. So that impulse is at time equals to t is equals to A. What it does if you multiply it by another function is it will give you the value of the function at time t is equals to A. That's the shifting property. And because it's only valid at that time instant, it will make everything else 0. So it will only give you the value of that function at that particular time. That's what is referred to as the shifting property. So to obtain the Laplace transform of this delta function, this is how we write it. I mean, this unit impulse function. So we use, we go back to the initial definition, which was, we did 1 over k u t minus a, because it's defined from a to a plus k. And then we also subtract the unit step function from t. Essentially, we are finding, we are taking this as a step function. So we have a unit step function starting at a. Imagine it going from here to infinity as 1. And then we subtract the function that starts from a plus k. So we only end up with this rectangular kind of arrangement. So we are finding that's what is represented by this. So to take, then if we take the transform of this using these different theorems that we have used before, we should end up with this here. Okay? Because we are going to, we will remove, okay, the transform of this is e to the minus as. Transform of this is again a plus k minus a plus k, yes. We factorize out e to the minus as and we end up with this. Now, remember we said for the unit impulse function, we have k as k tends to 0. I don't know if you remember this in math, in HSC mathematics, but when we have this kind of thing, we cannot substitute by k is equals to 0 here because we are going to get infinity. There is what is referred to as L'Hopital's rule, okay? And here we differentiate the numerator and the denominator, and then that's when we set k as k tends to 0, and we'll end up with, because we'll end up with SE, the minus ks over s, and as k tends to 0, then you'll have, first of all, the s's will cancel, but then this, as this ends, this exponential will go to, I mean, it will become e to the minus 0, which is 1, okay? So this term will become 1, so it means that the Laplace transform is, we are only left with e to the minus as, okay? So the Laplace transform of this unit impulse function is e to the minus as. You can go through this to convince yourself. It's not very difficult. So we have an example here. Find the Laplace transform. Determine the response of the damped mass spring system under a square wave modeled by this. Okay. We are going to use the other formula, the one that had double what? The 2y dx. We're going to, the way we solved our ODEs using Laplace. So we are going to replace this the 2y dt by s squared y plus 3sy plus 2y is In this case, you have to realize that our initial conditions say y is 0 is 0 and y, that both the initial values are 0. So that's why this is equal to this, because the initial values are all going to 0. And then the Laplace transform of this side, hope is obvious, is e to the minus s. So when you do leave ys on one side and divide by this quadratic equation, you end up with this sort of arrangement. Okay? When you factor out y and bring this equation on this side, this equation, you end up with this. So using partial fractions, we first ignore this. So let us first deal with this. So using partial fractions, this can be expanded to get these terms here. And we can find the inverse transform of all of them. From our table, we'll end up with this here, okay? But remember, this is multiplied by this. So we have to, y, so this was ft. Ft is the inverse of this. But our y is actually going to be ft minus 1 times ut minus 1, then minus ft minus 2 times ut minus 2. Because of this here, this term here. So to get what we have here, we actually have to expand. We have to make this ft. We have to make ft minus 1. How do we do that? We'll get a half. It doesn't have any t, so it will remain a half, minus e to the minus t minus 1 plus a half e minus 2 brackets t minus 1, which is this. Okay? And then minus, we have to also expand this, ft minus 2. Okay? ft minus 2, again, then we have to bring t minus 2 here and t minus 2 here as well. So minus 2 into t minus 2. Now, you need to work out how to get these coefficients. I think outside this class, I have the working for that term, but I think I will send it to you via email. Unfortunately, I did not upload it. I do not have it. I have it in a book, but it's a bit of a detailed expansion, but I want you to go through it. Israel, can you please, is Israel in the meeting? Israel? No? Or Joanne? Is Joanne here? Hey, none of the class reps has attended.
Hello. Yes, madam.
Israel, remind me.
Yes, I'm on.
Here.
Hey, both of you are here. I was worried. That kind of class. Anyway, you can both either just to remind me. I will take a photo of this and send it.
Okay.
Most likely I'll send to Israel because it's the one who has his phone number, so I can.
Okay, madam.
Yes. Yeah, so I'll send you this working and I want you to do it and try to follow it, and hopefully you'll be able to see how we get those coefficients, how we get these terms.
Yes, madam.
For the top one should be obvious to you. Like I said, every time you have a step function that starts at ut minus 1, it means everything before 1 is 0. So that this first part should be evident. But getting these other ones might not be as obvious. So because we do some manipulation, so I'm going to send actually I'm sending them right now, Israel. So maybe you'll share it just after the lecture. I don't want to do it after the lecture because I will forget and it will become an. I hope you can see it. I've just taken it with my phone and I used the funny colored pen, but okay. So please drive for it and try to go through it. If anyone doesn't understand how to get there, just contact me. The gist of it is that once we substitute for this ft minus 1 and ft minus 2, we are going to again introduce another term, because for this time between the interval 1 and 2, I need to be able to get ut minus 1. Like I need to get ft minus 1 into ut minus 1, and again ft minus 1 into ut minus 2. That's the way I get this interval. Okay, I need to have ft minus 1 multiplying both those intervals. Then I can get this. I can get this second term and this third term. But it might sound confusing here. Just try to go through the working. Israel will share with you. If there are any questions, you can ask maybe in the next lecture, or you could give me and I could go through it with you if anyone has an issue. I've just my email address. Yes?
Madam, in the T shifting, that expression of Laplace of ft, when you make a scenario where that t minus a is squared, do you still use the same function as the exponential negative as when the inside function of t minus a is squared?
Wait a minute. I'm not very good at multitasking. Let me first give you my email address. Yes, what were you saying? Sorry. Yes?
I was asking. Yes, that one.
Which one?
When you meet t minus the t shifting, that expression up.
This one.
When you meet, yes. If inside that expression of t minus a is squared, or it's a power, let me say power n, do we still use the same expression?
Which one is to the power?
That t minus a, that function.
No, because this T shifting only works if there are no powers. It only works for this when it's like this. So there are no powers. For you to use this function, the shifted ft minus a ut minus a should equal to e to the minus as fs, because the reason why we are bringing in this ft is because here we have fs times e to the minus s. So from here, we know that, this one actually translates to this. If I do the inverse transform, I should get ft, a is 1 here, ft minus 1, is u, t minus 1. That's it. It only applies to this, yes.
Thank you, madam.
You're welcome.
Yeah? My name is Elvis.
Yes, Elvis.
I'm kindly requesting you to maybe send, through the class rep, you send the reference textbooks, or where we can get some other numbers and other examples or exercise for practice.
Okay, I already sent this chapter, the reference chapter to Israel. He'll send it to you. I sent it this morning, so he'll send it to you.
Yes, I already shared the work, madam.
It's okay. Maybe he hasn't yet seen it. So, but you'll find that the book is not actually got from that book, but there are other examples. So, yeah. But you'll find that in the book, they don't expand these things. So I also had to go and look for it because initially it wasn't that clear. So that's why I wanted to give you that working. The book also only has this. They assume that everyone is, probably some kind of genius. I wasn't really happy about it. So anyway, another example. Find the response of the system in example 1 with a square wave replaced by a unit impulse at time t is equals to 1. Okay, so we have, this is it. You have this equation and you have a unit impulse. Okay, essentially, if you do, the initial values are also 0. That's what they are saying. It's just the same as the previous example, but now instead of step functions, instead of a square wave, we have an impulse, which is delta t minus 1 at t is equals to 1, so t minus 1. Hope that makes sense. So if you take the Laplace of both sides, okay, you do this, then you move, you divide this by this wave, and then you do the, what do they call it? I've forgotten the term in mathematics. You do this, essentially, you find that the roots, okay, of this equation. Yeah, then you do the what do they call it? The inverse Laplace transform. This one is fairly straightforward because if you have this here, then you yeah, from theorem 1, this is the inverse. So it's fairly straightforward. Once you have the what do they call it? Table 6.1, okay? Then you should be able to see that this is actually the inverse of these two. What the impulse function does is, again, shows you that at before 1, everything will be 0. Greater than 1, you'll have this. So I hope that's clear. Yeah, and this is what it looks like. Yeah, more in partial functions. Yeah, a note here. Wow. So if you have repeated, repeated, what do they call them? Repeated factors. So like in here, if you do your partial fractions and you end up with something like you have s minus a squared, okay? Then when you're creating partial fractions, you have to have these terms. You'll have one with s minus a squared and another one with s minus a. If the term is s minus a to the power 3 cubed, then when you're doing partial fractions, what you have to know is that you should also have another term. This should be A2, by the way. This was a mistake in the book. Make sure you change this to A2. So you should have one should be A3 over s minus a cubed. Another one should be A2 s minus a squared. Another one should be A1 s minus 1 the power a. That's just the way you have to do it in order to get the correct answer. I don't know if you remember these things of partial fractions, but those are some of the rules. Then if you don't have, if they're unrepeated, you have complex, say you have, I think s plus a squared, for instance, so that your solution is going to be a complex number. I mean, then your solution will have complex numbers, but they don't really come in. You don't have to worry so much about this. This is a detail, which would, when you come to applications of these things, maybe in third year, if you're doing digital signal processing, then you have to know, but here it doesn't really matter because let's look at an example, because it will work itself out. If you do the plus, it's just everything will work out. You don't really care. But if you're doing partial fractions, please don't forget, if your partial fraction ends up being of this format, make sure that you have a2 over s minus a squared and a1 over s minus a. Just make sure you do that. Because if you don't, your partial fractions will not work out. You'll end up failing to break up your expression into partial fractions. So don't forget to do that. We have an example here. Again, we are given this differential equation, non-homogeneous. We're given what our RT is, it's 10 sine 2t, and then we're given intervals, okay? So it's 0 between, RT is equals to 10 sine 2t between 0 and pi, and 0 for t greater than pi, okay? Initial values, y0 is 1, the derivative, first derivative at 0 is equals to minus 5. So again, we use that same equation. But now we have sy squared minus s plus 5 because of these initial values are there now. So we have minus s here and 5 here. And then we have 2s. For this, we have 2sy minus 1. And then here we have 2y. And then again, getting the Laplace for rt, it's a sign. So we get this. But because of this, okay, it's 0 between t and pi. What does that tell us is that there's some kind of a step function, and this is how we've represented it. So we have 1 minus e to the minus pi s. Okay. So again, collecting like terms, you end up with this and this. So for which one? For this one, this is how we solve it. Okay, I hope you remember what we did last time. We completed the squares and then we wrote it in this manner. Then because we have s plus 1 squared, we also write the top part in this manner. So we make it s plus 1 because it's minus 3 here. We end up with minus 4 here. And then we can write it in terms of a cosine and a sine. Now this is where we apply what I've just told you. Now you end up with this one where you have 20 over s squared plus 4 into s squared plus 2s plus 2. You can't simplify this any further. So anytime you have a square in here, okay, then the top, when you're doing partial squares, partial fractions, you have to, the numerator should be as plus b. One term should have times s, essentially, is what we are saying. For this one, that's why they also put for this one ms plus n, because there's a squared. It's only when you have been able to simplify it like this one, and no, the other example we had before. If we had been able to split this set to s plus 1 into s plus 2, that's when you can have a and b. But once you can't simplify it more, then the numerator should have an s in it, okay? And then you do your algebra here, and you should end up with the values of a, b, m, and n, and substitute them, and then you should be able to get the inverse, the transforms of these, okay? This one, again, you have a cosine plus a sine. Same thing here as well, but it's just you do some manipulation before you get your answer. So the sum of the inverse and 7, so the sum of this and the sum of this, because this is what we did first, sometimes I think are going to cancel, so you end up with this expression, okay, as your answer. I think there were 3. Okay, so we have done this and we have done this. Now there's this one. You'll see that this one is exactly the same as this, except that it has this e to the minus pi s. If we use that shifting theorem again, we just know that this is going to, we just bring in that e minus this factor, okay? And then we do our substitutions and we'll end up with, for t greater than pi, we will add it, and this is what you end up with your solution. Okay, so please go through these steps. Now that I'm going through, we cannot go through everything. Just go back and try to do the additions and the manipulations and the transforms, and ideally you should be able to work up to these answers. The trick for this one was really to figure out that every time you cannot simplify, if you end up with a square in the denominator, the numerator should have an s in it, some as plus b or cs plus d, whatever numbers you choose to use, doesn't really matter. We need to move on. So there's what is the convolution integral. This one has to do with multiplication of transforms. So we already said that the Laplace transform is linear, but if someone asks you what the Laplace transform of LF, like if the Laplace transform of LF times LG, is it equal to the Laplace transform of F and G? You'd think it is, but no, this doesn't hold. And there's a simple proof here. You can go through it. We have F is equals to ET and G is equals to 1. So the Laplace transform of fg is the Laplace transform of et because it's et times 1. And you'll find that the Laplace transform of et is 1 over s minus 1. However, the Laplace transform of LF, which is again et, is going to be 1 over s minus 1. And the Laplace transform of g is 1 over s. So LF times LG is 1 over s squared minus s, which is not equal to 1 over, which is not equal to this, the Laplace transform of fg. So the way it's done, this brings in what is called convolution. Okay. So the Laplace transform of LF times LG is equivalent to the Laplace transform of the convolution. This is what is called convolution of these f and g in the time domain. So convolution is denoted by this star, asterisk, and it's given by this. It's an integration. We denote it by, this is how it's usually written. So you integrate from 0 to t, some f tau, and g is shifted by tau. You have t minus tau and d tau. So if two functions f and g satisfy the existence theorem for Laplace, then their transforms exist, then the transform of their product, yeah, h is equals to fg is the transform of h. Let's see an example. I think it will help. So if we have hs, okay, is given by 1 over s minus a times s, and they tell us to find ht. By inspection, this is the same as 1 over s times 1 over s minus a. We know what those are, okay? The transform of 1 over s minus a is e to the power at. The inverse transform. And 1 over s is 1, okay? So if we want to find, using these two, if we get their convolution, we will be able to find what ht is. And that's what is done here, okay? So we get convolution of EAT and 1, which is going to be, if you substitute e to the a tau times 1 d tau, and then if you integrate, you should get this. And yeah, as a way to calculate, to check this, if it's correct, if you take the Laplace transform of this, you will end up with 1 over a into 1 over s minus a minus 1 over s. If you do the manipulations, you'll end up with 1 over s minus a times 1 over s, which is essentially the Laplace transform of EAT times the Laplace transform of 1. This is a kind of proof, proving that the Laplace transform of LF times LG is equal to the convolution of their inverse transforms. It's a mouthful, but yeah. And convolution is this integral, okay? You get one term in terms of tau, delay the other one by tau, and then integrate with respect to tau from 0 to t. That's how you solve the convolution. Here's another example. You have a given hs and you're told to find ht. By inspection, this looks like 1 over s. I mean, this is 1 over s squared plus omega squared times 1 over s plus omega squared, 1 over s squared plus omega squared, which we know is sine omega t over omega. Okay? So how do we find ht? We're going to get the convolution of these two. And yeah, so it's going to be sine omega tau, sine omega t minus tau d tau. This is going to be this whole thing actually. If you look at it, it's the same as cos, yeah, one of those, I think it's cos a plus b plus cos a minus b, something like that. If you look at those trigonometric identities, which is what they did here. So you end up with this term and this term, okay? Then you integrate. And if you integrate and do your substitutions, you should end up with this here. Just a note, when you're doing this really confused me because I integrated this and I got sine omega, 2 omega tau minus omega t divided by 2 omega. And I was like, how did they end up with this? But just stick with it. If you do all the substitutions, you'll end up with the same answer. I honestly think they made a mistake with this term. But when I did my substitutions, I ended up with this answer. So if you do this, just stick with the sine 2 omega tau. If you integrate this, just stick with the sine omega, 2 omega tau minus omega t and do your substitutions. It will work out because it really wasted a lot of my time. Maybe there's something I don't know, but I think they made a mistake here. That's just my thinking.
Excuse me.
Yes.
Excuse me, madam.
Mm-hmm.
I'm not really satisfied with the flow of your pointer, of the pointer and the display. There's a mismatch. Yeah, what you're displaying can't really relate with the pointer. So sometimes, I don't know if it is my network probe, but I've missed a bit of the convolution. Let's, if you don't mind, if we go back a bit, how the
convolution, you can see it here. Even here it is, you can see it. Because if I convolve this one with this one, okay, maybe I'll go back. Here, this is convolution. I want to convolve F with G, okay?
Okay.
F tau, and for G, I replace what would have been T by T minus tau, and then I integrate with respect to tau. That is convolution, it's an integral.
All right, thank you.
So all we are doing here is just replacing that. If this was our F, also replace T by tau. And if this was our G, T is now T minus tau, and we integrate with respect to tau. And we are integrating our limits as 0 to T. So once you do that integration, you should end up with this answer. Okay. This is a proof. For those of you who are interested, please go through it. I'm not going to spend time on it because I will not ask about it. Just learn what the formula is, and yeah, it will be good. Proof of the theorem. Yeah. Okay, these are some interesting properties of the convolution. It's commutative, distributive, whatever. Please go through them. Yeah, this I also found interesting. You'd expect that if you convolve a function f by 1, you'll get f, but it isn't true, and they show you why. You'll see this, you will see that you get, if you convolve t with 1, you'll end up with a half t squared, which is not equals to t, obviously. Yeah. And also if you convolve two functions, you might end up with a value that's not. Unlike multiplication, where when you multiply two functions, you always end up with, I think, two positive functions anyway. You always end up with a value greater than 0. This is just pointing out that it might not. So if you have sine t convolved with sine t, you end up with some kind of cosine. So part of it will not be positive. This is more or less like this is exactly what we did on the previous slide, actually. Sine omega t. I don't know why they repeated it here. Okay, this one is an example, I think. So in an undamped mass spring system, resonance occurs if the frequency of the driving force equals the natural frequency of the system. So the model is going to be given by this equation, differential equation, okay? Omega naught is equals to k over m, where k is the spring constant and m is the mass of the body attached to the spring. We assume y is the initial value. Yeah, initial values are both 0 for simplicity. So when we take the Laplace transform of this, it's essentially going to be s squared y plus omega squared y, because the initial values are 0. And then the Laplace transform of this is going to be k omega naught over s squared plus omega squared. And then we'll have to divide by s squared plus omega naught squared. So we'll end up with this squared. Okay, so the issue is then, yeah, how to solve that. So from example 2, the one we have just done, yes. Okay, because this is a multiplication of, if you look at this, it's s squared plus omega naught over s squared plus omega naught squared is a multiplication of two sine functions. So that's why they're saying from this example, the answer we got here, you can directly get the answer of, yeah. Actually, they repeated it here. So from here, all we're going to do is multiply by our omega naught here times t cos omega naught t, and then our sine omega t. Again, if you multiply by omega naught, the omegas will cancel. That's why it isn't here. And then divide by this factor. I'm sorry, multiply by it to get the answer. So this comes from the other one, and it's also again an application of the convolution integral. Please, yeah, just go through it. It should work out. And then application to non-homogeneous linear equations. I think we'll look at an example. So using convolution, determine the response of the damped mass spring system modeled by this equation. Okay, initial values are 0. RT is equals to 1 if 1 is less than T, which is less than 2, and 0 otherwise. Okay, so this system has an input driving force that acts only for some time. This just tells us that we have some kind of state functions involved, which is what is shown by this square here, this square wave here. Yeah, so earlier we solved this using partial fractions. Now we're going to use the convolution integral. If you do the Laplace transform of this, you'll end up with this same thing. So it's going to be s squared plus 3s plus 2, because the initial values are all 0. And then that will equal to 1 over s plus 1 minus 1 over s. Remember, this is going to be, our function is going to be multiplied by these two state functions, ut minus 1 and ut minus 2, because of this rule, because of this condition. Okay, so that's why we have this on this side. And yeah, so when you, oh no, this is just an expansion of this. QS is, when you take the Laplace transform of this and collect the like terms, it's what you end up with, that equation. So it's this. These are the partial fractions, so you end up with QT. If you do the integral, the inverse, you end up with these two. Okay. So hence the convolution integral. So we'll have QT minus 1 times R1. RT is equals to 1. So that's the one they're talking about here. So QT minus tau times 1 d tau. This is convolution now. We're convolving that to get YT. And yeah, when you work out the convolution, you will end, the integration, sorry. The integration, you'll end up with this. Yeah. So now, again, the limits come in. So if t is equals to 0, so we've gotten this expression from our convolution. But now we need to figure out what are the values of this of yt for the different intervals. So less than t, like we said, everything will be 0. Okay. When t is equals to 1, we need to go in and between 1 and 2, we need to go in and substitute those values in here. Okay. So we have minus t minus tau and 2t minus tau. So when our tau is 1, tau is 1, okay, and t is 1, we'll end up with 1 minus 1. So we'll end up with e to the minus 0, and here minus a half minus 0. And then substituting in again, we'll end up with minus e to the minus t minus 1 and a half e minus 2 t minus 1. When we expand all this, then this will be 1 minus a half. That's why we end up with a half here. And then minus e to the minus t minus 1 and a half e to the minus, essentially this is substituting. Then if t is greater than 2, again, we have to now integrate from tau is equals to 1 to 2 in our equations before. So we will end up with a situation where we have t minus 2 minus a half e minus 2 minus t2, and then also subtracting this term because we are integrating from 1 to 2. It's just substituting these limits in here. And we end up with these expressions. And I think I think it's the same figure that we had earlier. Yeah. So, yes, figure 143. This is what it would look like. I will not ask you to sketch any of these, but I think it's good to just visualize what it looks like at the end of the day. Okay. So another application of these convolution integrals is we have equations like this. This is the Volterra integral equation of the second kind. So you have yt minus an integral from 0 to 2 of y tau sine t minus tau d tau. So it's like a convolution. Okay. So this should be clear that you have y minus, this is a convolution, which is equals to some function, to t. So taking the Laplace transform of this, we'll know that here we have ys. Because this is a convolution, we know that the Laplace transform is going to be the product of the two transform of each of these. So it's equal to minus ys times the Laplace transform of sine t, which is 1 over s squared plus 1. And we can simplify that. And then we also know what that Laplace transform of t is, which is 1 over s squared. So when we sum this part, like when we collect, as in we take out the ys and sum these two, which is 1 minus 1 over s squared, we'll end up with this. And then equate it to 1 over s squared. Then we can easily solve it. And we end up with this. And then we can now get the inverse. Okay, the inverse Laplace transform, which 1 over s squared is t, and 1 over s to the power 4 is t to the power 3 divided by 6. Again, this is by looking at the tables, because the Laplace transform of t to the power 3 should actually be 3 factorial, I think, times t to the power 3. But now, because we don't have the factorial here, that's why we have to divide by 6, because it's just 1 over s to the power 4. We should have had here 6, actually 3 should have had here 3 factorial over s to the power 4. But because it's just 1 over s to the power 4, then we have to divide by 3 factorial to cater for the fact that the 3 factorial is missing here. So for some of these, because you recognize that this is a convolution, then you can use this. You can use the fact that the Laplace transform of convolution is the same as multiplication of the two, the multiplication of the Laplace function of the individual. I mean, the Laplace transform of the individual functions. So that's how that helps. And this example is also similar, very similar. So again, you have y. Again, recognize that this is a Laplace transform, so it's the same as minus 1 plus t, which is this, convolved with y, okay? And then, which is equals to 1 minus sine ht. And then, yeah. Once you recognize this, then you can replace this with a multiplication in the S domain. So we take the Laplace transform. The rest is really substitutions and then inverse transform. So please go through this example. Yeah. I think I'll have to stop here. We have 6 minutes, but this integration and differentiation, I don't think we'll go through. Next time we shall start with system of ODEs, what we shall complete, and then we shall start Fourier transforms. Because I didn't see this in your syllabus, even if it is here. If we had time, I'd have gone through it, but next week we shall look at what? We shall start with system of ODEs, and then we shall start Fourier transform.
Hello, madam.
Yes?
Good morning, madam.
Good morning.
I'm Chamfumba Dennis.
Yes, Dennis?
I'm having a concern. The rate at which you're teaching is actually, I'm not following very well that stuff.
But you see, every
and
time
I have a suggestion.
Every time I did something, I've been asking, does it understand? Questions. I cannot.
Yeah, no.
Yeah.
Okay, madam, my point, that one is there, but the major, I had a suggestion.
Hello?
Like, is it possible for you to, because for me, I'm not. So it's my suggestion that if possible, and you try to simplify it sometimes, because I'm seeing I'm getting a lot of coverage within a short period of time. End up confusing. I end up getting confused when I'm going to try practice. I see that I have to do a lot of work, like teaching myself everything.
For instance,
but if you try to simplify,
what terms are difficult? Because you see, that's why you have to ask when I'm teaching. Because now when you tell me simplify, that is simplify what? Your suggestion is too vague to be used. That's why when I'm asking at that point, remember when the other gentleman, I don't remember the name was, says that, oh, madam, I haven't understood what you mean by the function at delay a unit step function, anything below. Then I can explain that. But now I do not know. So for instance, what term? Because if you tell me at the end, it becomes, it's very difficult for me to help you. But if at that you say, madam, please go back to a convolution. But the key thing that you have to understand, I forgot your name, is it Dennis? The key thing you have to understand is that there's a lot of integration. And that's why I told Israel, the first thing you should do, go and remember your trigonometric identities. Do your integration. Know how to integrate functions. For Laplacian, you need to understand those tables. Okay, you need to get those tables and know what the Laplacian transform of sine is, of t, of exponential, because everything else that we do, we keep saying, this looks familiar. So please, the inverse is going to be s, is going to be t squared, or is going to be sine. Then everything we have to work out is an integral. It's a lot of integration and differentiation and application of the theorems we have learned. But my suggestion is try to go back and go through them. If you have any issue, I've even put my email here in the what do you call it, in the group, in the chat. Feel free to send me an email, but don't send me an email and say, Madam, I don't understand convolution. No. Try to do the example. Then you can even take a photograph of the picture and say, I am stuck here. I can know what you have done wrong, okay? Or what you don't understand. Yes, but when you tell me I am stuck, I cannot help you. Stuck where? Do you get my point? But when you do an example and say, Madam, the answer is saying in 5 minutes, I don't see how you end up with science. When I'm integrating, I'm getting 50. Then we can talk. I say, okay, maybe the mistake you're making is here. Can you watch this video? Can you see this working here and see if you get it? There we can help. And that's why at the end of each thing I was trying. Because at that point where I have just explained, when you ask the question, first of all, you help also other students, but you also learn. And also maybe you help me understand what it is that you don't understand. But when I come at the end and you tell me I don't understand, simply, that is too vague. I'm not saying you've done something wrong, but please feel free. I don't mind people asking questions. Ask that question. I cannot help you. But I want you to go back and try to do the examples. If you cannot work through them, just take a photograph and say, Madam, I went through this thing, but when I reached here, I did not understand. I cannot move beyond this. This person is getting this. Me, I cannot move beyond this. How did they integrate this?
Okay, Madam. Thank you.
Talk. Yes. Feel free to send an email anytime. I will respond. Okay. If I get too many emails from students, I will address it in class.
Thank you.
You're welcome. Someone else was asking, saying something.
Excuse me, Madam.
Hello?
Hello, Bichina.
Excuse me, Madam.
Yes?
Madam, if you're given a section full of an ordinary differential, is there a limit of which method to use? Or
yeah, but for instance, for this course, I will definitely ask you to use Laplace. I will not ask you to use the method you used in first year. Because now what we are learning is how to use Laplace to solve these equations. So for this particular for this particular course, don't start solving characteristic equations. I will not give you a mark.
No, Madam, I'm meaning like if I'm using maybe convolution and the other first method.
Oh, for those ones, it will depend. If the question asks you to use convolution, then you have to use convolution. But if it's open, then use whichever method it works for you. Because at the so unless the question specifically says use convolution, okay, to solve this, ideally you should be free to use whichever method.
Thank you.
You're welcome.
Excuse me, Madam.
Yes.
Hello, comrade. So, Madam, there are some proof works we did last lecture concerning some of the theorems. Are they also examined or they are not examined too?
Like which ones? It's the same thing. Which ones?
Like we're defining some theorems the previous lecture. Like we had theorems today and we're proving how they come about. So my question is, are those theorems, are those proof works examined or we don't need to get them?
You understand them. Try to understand them. But it is unlikely that I'll ask you to prove.
Okay.
I'll probably ask you to apply more than to prove.
And then there are these graphs we were looking at, the impulsive graphs we looked at today. Do we sketch them in the exam or we don't sketch them? They are given.
I will not ask you to sketch them, but I will ask you to give me those solutions. Ideally, you sketch them, but I won't ask you because I've not taught you how to sketch them. I don't know if you have the background to sketch them. Ideally, you should, because you learn how to sketch these things in HSC, and I don't know if last year you also learned them. But I will not ask you to sketch them, but I will ask you those questions, similar questions, as in terms of find the limits of the different, like if I tell you a signal is say we have excitation, or the input is T between 1 and 2 and T squared between 2 and 3, that kind of thing. I may not ask you to sketch it, but probably you need, if you're a visual person, you would need to visualize it. I don't think you need it to work out, but yeah, I'll not ask you, it will not have marks, the sketching.
Okay. Thank you, madam.
You're welcome. But you don't have to thank me. Eh? Hey, everyone calling, who is speaking has to thank me. I am paid to actually teach you. So don't feel the need to thank me, please. It's not necessary. Are there any other questions? Maybe another thing I wanted to address, and maybe you'll tell those people who are not here. The good thing is the lecture is being recorded. When you people are communicating with lecturers, just try not to be too should I say familiar? Because you cannot send a lecturer whom you don't even know and you say good morning, dear. That is very wrong. This I'm just teaching you, because when you go to apply for jobs, you're going to do the same things. When you're applying for internships, you'll do the same things. When you're talking to someone you don't know, who is in a capacity where it might be like your boss or someone senior, you don't, these dear things, you do them for your family, your friends, anyone else. It should be good morning. You can say good morning, madam, good morning, sir, or dear madam, dear sir, or yeah, but not hello, not good morning, dear, not hello, dear, not hi, dear. No. Unless someone, that other person is the one who writes to you that way. But I was worried because someone contacted me that way. And sometimes when you're girls, you're contacting male lecturers, they might get ideas. Other people might just be put off. So for me, if it's a job and you write for me, good morning, dear, most likely you're not going to hear from me. But just learn how to communicate professionally. So you could just say good morning, Dr. NABUUMA, and start from there. But when you start a message, good morning, dear, I'm like, is this a serious student? So please try to be formal in your communication. It also reflects on you because it makes it seem like you're very unserious. Okay? So if you're communicating with me, please, you can call me Dr. Madam, you can call me Doctor, you can call me, Miss NABUUMA, I don't care. But just don't call me dear. Thank you. Does anyone else have a question? Okay, so we shall meet again on Monday. Have a nice weekend.